What is Kubernetes? Today we're going to unpack this powerful platform and understand why it's become a popular tool for scaling modern software stacks. So what exactly is Kubernetes? At its core, Kubernetes is an open source platform designed to automate the deployment, scaling, and management of containerized applications. Think of it as a conductor for your applications, especially those composed of hundreds or even thousands of individual containerized components. Originally created by Google, Kubernetes is a popular solution for managing complex distributed applications across various environments, from physical machines to virtual ones, and from on-premise setups to cloud platforms. Now, why has Kubernetes become so essential? Well, it all comes down to the rise of microservices architectures. As applications have grown more complex, developers have started breaking them down into smaller, independent services. These microservices are typically packaged in containers, which provide an ideal environment for running them. But here's the catch. As applications scale up, managing all these containers manually becomes a nightmare. That's where Kubernetes steps in. It offers a streamlined approach to container orchestration. Let's break down the key benefits that Kubernetes brings to the table. First, there's high availability. Downtime is costly. Kubernetes helps our applications to remain accessible with minimal interruptions. It does this by automatically restarting failed containers, distributing load across multiple instances, and offering self-healing capabilities. Next, we have scalability. As our user base grows, the applications needs to handle increased load. Kubernetes makes it easy to scale our applications up or down in response to changing demand. This flexibility ensures optimal performance and resource utilization. Now let's dive into the architecture of Kubernetes to understand how it provides these benefits. A typical Kubernetes cluster consists of the control plane and multiple worker nodes. The worker nodes are the workhorses of the cluster. They are responsible for running the containers that make up our applications. The number of containers on each worker node depends on factors like resource requirements and overall workload distribution. Each worker runs a process called kubelet, which acts as a local agent that enables communication and coordination within the cluster. The control plane, on the other hand, serves as the command center. It orchestrates and manages the entire cluster. It runs several critical Kubernetes processes. First, there's the API server. Think of it as the central communication hub of the cluster. It's the entry point for various Kubernetes clients, including user interfaces, APIs for automation, and command line tools. Next, we have the controller manager. This component maintains the desired state of the cluster. It continuously monitors the cluster's health, identifies any deviations from the desired state, and takes corrective actions. Then there's the scheduler. It distributes incoming containers across the worker nodes based on resource availability and specific requirements. Underpinning all of this is etcd. It's a robust key value store that serves as the persistent memory of the cluster. It securely stores all configuration data and the real-time status of each node and container. To enable seamless communication between nodes, Kubernetes uses a virtual network that interconnects all nodes within the cluster. This virtual network abstracts away the underlying physical infrastructure and presents the cluster as a unified computing resource. In terms of resource allocation, worker nodes typically have more CPU, memory, and storage compared to the control plane nodes. This is because they bear the brunt of the workload by running numerous application containers. Control plane nodes, while running fewer processes, are critical for cluster operations. In production environments, it's common to deploy multiple control planes for redundancy and fault tolerance. Now let's visualize how these components work together using a practical example of a web application that uses a database. At the heart of Kubernetes' resource model is the pod. A pod is the smallest deployable unit in Kubernetes. It's an abstraction layer on top of one or more containers that logically belong together. In a web application scenario, we would have an application pod hosting the web server and a database pod managing the database. Pods in Kubernetes are ephemeral. If a pod fails or needs to be rescheduled, Kubernetes will automatically create a new one to replace it. However, this new pod might have a different IP address, which can pose a challenge for inter-application communication. To address this, Kubernetes introduced the concept of services. A service provides a stable IP address and DNS name that acts as an internal load balancer for a group of pods. Even if individual pods are recreated, the service IP address remains constant, ensuring consistent communication. For a web application to be accessible to users outside the cluster, we need to expose it to the internet. Kubernetes offers external services for this purpose. It opens up a specific port on the cluster's network and routes incoming traffic to the appropriate backend pods. While external services technically expose our application, the default URLs they provide can be complex and not very user-friendly. This is where Kubernetes Ingress comes into play. Ingress acts as a smart reverse proxy, allowing you to define rules for routing external traffic to specific services within the cluster based on the request URL. Kubernetes also provides mechanisms for managing applications configuration data. Config maps stores configuration data like database connection URLs or API endpoints, while secret stores confidential data like passwords and API keys. To enhance the resilience and availability of a web application, we can leverage Kubernetes' ability to create multiple replicas of our pods. Kubernetes offers two primary mechanisms for managing pod replicas: deployments and stateful sets. Deployments are ideal for stateless applications, like a web server, where each replica is interchangeable. We can define a deployment that specifies the desired number of replicas for our application pod, and Kubernetes will ensure that number is always running. Now let's talk about keeping your data safe and sound in Kubernetes. Kubernetes Volumes provides a mechanism for abstracting storage from the lifecycle of pods. It allows us to mount external storage directly into the pods. This is useful for scenarios where data needs to be persisted even if a pod is deleted or recreated. For stateful applications like databases, Kubernetes provides stateful sets. These build upon the functionality of deployments, but offer additional features tailored for applications that require persistent storage and careful management of data consistency across replicas. While stateful set offers a way to manage stateful applications like databases within Kubernetes, setting up and operating databases in Kubernetes can be complex and require specialized knowledge. Many organizations opt for a hybrid approach. Instead of running databases directly in Kubernetes, they might host their databases externally, perhaps on dedicated database as a service platforms. They then connect their applications running within Kubernetes to these external databases. This hybrid approach offers a balance. It allows organizations to leverage the benefits of container orchestration for their applications while avoiding the complexity of managing stateful applications like databases within the Kubernetes environment. It's a practical solution that many teams find effective, especially when they have particularly demanding database requirements. So when should Kubernetes be used? As with many things in software engineering, it's all about trade-offs. On the upside, Kubernetes is scalable and highly available. It's packed with features like self-healing, automatic rollbacks, and horizontal scaling. It allows us to quickly scale applications up and down as needed to respond to changes in demand. Kubernetes is also portable, enabling consistent and reliable deployment and management of applications regardless of underlying infrastructure, whether on-premise, in a public cloud, or in a hybrid environment. On the downside, complexity is the number one drawback. Kubernetes is complex to set up and operate. It comes with a high upfront cost, especially for organizations new to container orchestration. It requires a high level of expertise and resources to set up and manage a production environment. Cost is also a drawback, as Kubernetes requires a certain minimum level of resources to run in order to support all its features, likely making it overkill for many smaller organizations. One popular option that strikes a reasonable balance is offloading the management of the control plane to a managed Kubernetes service, which cloud providers offer. Some popular ones are Amazon EKS, GKE on Google Cloud, and AKS on Azure. These services allow organizations to run Kubernetes applications without worrying about the underlying infrastructure. They take care of tasks that require deep expertise, like setting up and configuring the control plane, scaling the cluster, and providing ongoing maintenance and support. This can be a reasonable option for mid-sized organizations. For smaller organizations, the complexity and resource requirements of Kubernetes might outweigh its benefits for smaller-scale deployments. If you like our videos, you might like our system design newsletter as well. It covers topics and trends in large-scale system design, trusted by 1 million readers. Subscribe at blog.bytego.com.